I think the easiest way to learn calculus of variations is to do an example problem. So here's an example where f has to satisfy that its value at 0 is 0 and its value at 1 is 1, and we want to find such a function that minimizes this integral. Now, what does that mean? Well, first, it has to be a function that connects 0, 0 to 1, 1, but you need it to be such that it doesn't go too high. You don't want it to go like that, because in that case fx squared will be very big. So in order to make this small, you might think, oh, maybe I should do something like almost 0 and then suddenly shoot up to 1. But then the problem with this is that the derivative will now become very big, so its integration of the second one will be pretty big. Now, at the end of this lecture, I will actually show you what function minimizes this, and you'll see that in that case it goes something like this, and I can actually give you the exact formula for that function. That's our goal. Now, if you have a function of, so L is like a function of functions, which gives you back a number after doing this integral, right? If you have a function which takes in function as its input and gives you out a number, that's called a functional. On the other hand, there are some function of functions where it takes in a function and it gives you back another function, not another number, but it gives you a function. In that case, that's called an operator. So from now on, I'm going to talk about this. I'm going to call this left side as a functional. And moreover, you can really think of this functional as a functional of just f, and that would be fine, because even if I didn't write this down, L of f of x being this way is perfectly okay, because if you know f, you can differentiate it and plug it in here, right? But just for some kind of equation that we are going to use later, it's helpful to have f prime explicitly in here to denote that the functional that we work with only depends on the function itself and its derivative. Yeah, but I just want you to know that this functional is just a functional of the function f. Okay, so what is the core idea here? Well, the core idea is to vary the function by another function g of x as follows. In other words, you replace f of x by fx plus some multiple of g of x, where t is some kind of a constant. And because you're replacing f by this, the second part will be filled in by the derivative of this, but you're differentiating by x, and since t is just a constant multiple, if you differentiate this, you're going to get f prime plus t times g prime of x, right? If you view the functional in this way, you can see that this is really a function of t. And once you have a function of t, what we're going to do is very similar to the directional derivative in multivariable calculus. In multivariable calculus, if you have a function, a multivariable function, the directional derivative is defined as you evaluate the function at a and also evaluate the function at a, and then you move a little bit towards to the direction of v, and then you take the difference and divide by t and send t going to 0. That's the definition of the directional derivative. And because this is a 0 over 0 type limit, you can use the L'Hopital's and you differentiate the top and bottom by t. If you differentiate t by t, it's 1. The top one, if you differentiate fa by t, because this doesn't have any t in there, that's going to be 0. So you end up having just the derivative of this. And then you can plug in t equals to 0 without any problem. So plugging in t equal to 0 will be the evaluation of this limit. So finding the directional derivative of some function in the direction v is differentiate by t and then plug in t equal to 0. So that's exactly what we want to do. We want to differentiate this functional as a function of t and plug in t equals to 0. And then, because we're looking for the minimum, if the function that we have is indeed a minimum, then this functional differentiated by t and plugging in t equal to 0 should be equal to 0 because it's like the critical point. Yeah, it's the minimum. So its derivative has to be 0 for any function g of x. Now, there is actually some condition on g of x. It's not any function. Because we are replacing f by this h, right? And you still want h of 0 to be 0 and h of 1 to be 1. See, if you plug in 1 into this identity and you want f of 1 to be 1 and h of 1 also to be 1, then subtracting these two forces g of 1 to be 0. And therefore, you see that when you vary fx by another function, this another function g of x has to satisfy these two conditions. G of 0 has to be 0 and g of 1 has to be 0. And moreover, there's some other technical properties that you probably want g to satisfy. And actually, we will just say g of x is smooth, and that should be fine. Smooth means it's infinitely differentiable. Okay, so let's get to work. We will actually differentiate the functional by t, and that means the derivative is taken, it goes to inside. Let's just assume that derivative can't go inside. And when you see these functions as functions of t, it's just simple chain rule, right? So you differentiate the outside function, so it's twice of this. And then the inside function has to be pulled out and differentiated. When you take this inside function and differentiate by t, you just get the coefficient g of x. That's why you have g of x, right? Whereas this 2 times fx plus tgx is the derivative of the outside function. And then same thing can be done here. Again, the derivative of the inside function creates g prime of x. Now, we can break up the two integral. So the single integral can be broken up to two integrals. And for the second integral, we can apply the integration by parts. So we apply the integration by parts, so we integrate g prime of x, whereas the other one that we did not integrate will get differentiated. And then you have to plug in the endpoints, 1, 0 here. But because of the condition that g of 1 has to be 0 and g of 0 has to be 0, this part will actually become 0. And now that these two are both integration from 0 to 1, we can put them together again and also factor the 2g of x, and we have the following. Okay, so that's the derivative. Now we plug in t equals to 0, and we get this integral. And we now see that if f is indeed the minimum of the functional L, then it better have that this integral should equal to 0. So write that down, and let's think about what this means. If this is indeed equal to 0 for any differentiable function g of x, with g of 0 equal to 0 and g of 1 equals to 0, you could kind of see intuitively that there's no other choice but for this to be equal to 0. Now, this actually can be done rigorously using analysis, and if you assume that f can be differentiated many times and its value is bounded. Of course, 0 to 1 is a compact interval in math language, and there's some other things that you can do. And for math majors, you would see that you can show that this part here has to be equal to 0 almost everywhere, and then assuming that this is differentiable almost everywhere, 0 should mean that this is identically equal to 0. But you don't have to be a math major to know that. It's just that if you have some function whose multiplication by any function and integration from 0 to 1 is 0, the only way that could be done is if this is identically equal to 0 between 0 to 1. Okay, so if that kind of makes sense, then let's not go too deep. Let's not become math majors. Just let's accept that this is true. Okay, so that means this has to be 0. In other words, f of x must be a solution to this differential equation. See, y double prime with a minus plus y, right, equals to 0, with y of 0 equal to 0 and y of 1 equal to 1. And this is a really nice exercise in ODEs. So if you took one semester of ODEs, then you would know that the characteristic equation for this one is negative r squared plus 1, whose solution is 1 and negative 1. So e to the x and e to the negative x are the two solutions, and then you apply the boundary conditions and you do all the work, and the end result is that you're going to have this as the solution. And if I actually draw the graph, this is drawn from negative to 2, but really if you look at the value between 0 to 1, it's somewhat like this. You may notice that this is what people call the sine hyperbolic function with some coefficient, but it's something like that. Okay, so that is the answer to our problem. Okay, let's recap. See, we originally had this problem, f of 0 has to be 0 and f of 1 has to be 1, and you want to minimize this functional. And to use the standard notation, people often use q rather than f, so that q of 0 is 0 and q of 1 is 1, and you want to minimize L of q prime as this. And the thing inside this integrand, usually people denote that by L, okay? And L comes from Lagrangian. People call this integrand as Lagrangian. Okay, so this Lagrangian is q squared plus q prime squared, and at some point in our calculation we did calculate the L differentiated by q and L differentiated by q prime. See, if you differentiate this by q prime, for a moment just forget the fact that q and q primes are related. Just think of q as one variable and q prime as like p or some y or some other variable. Then you can talk about differentiating L by q prime, treating q as a constant, so that's like 2q prime. And if you go back to our previous calculation when we differentiated by t, you see that 2q actually happened right here. It's 2 times q, and that's because we're doing the derivative of the outside function. See, q squared is the outside function, so when you differentiate this you get 2q, and indeed you have 2q here. On the other hand, you have 2q prime in our previous calculation. So these were calculated, although you didn't notice it. And not only that, once this was done, we had to apply the integration by parts on the second part, so that this actually had to be differentiated yet one more time in the x direction with respect to x, and you had to put a minus. So what happened was that integration by parts gave us the following equation. This was multiplied by g of x, and we integrated over 0 to 1, and the argument said that, oh, the only way that this integral can be 0 is when this is equal to 0, right? And this formula here would be universal. We just worked it out for this specific case, but if L is a function of q and q prime, then always the same kind of procedure that we follow will always lead to this equation, and therefore this equation has a name. It's called the Euler-Lagrange equation. And the left side is also called the functional derivative of this functional, and it's written as delta L over delta F. Now in general, you can say that if you have any functional of q and q prime, then it's going to be maximized or minimized when the Euler-Lagrange equations hold. And moreover, if you have some more derivatives, so if your L is a function of q prime and q double prime, then for each partial derivatives you need to, each subsequent differentiation by the derivatives, you need to do integration by parts. So for this one, you need to do integration by parts twice. So you will end up having to differentiate by x twice, and because it's negative of negative, this time it's plus. And if you had q triple prime, then it will be another term here with the minus differentiate by x 3 times, and then partial of L over partial of q triple prime. So that's how you write down the Euler-Poisson equation in general, and they all rely on integration by parts. Okay, so now we have understood what calculus of variations is. We can now talk about principle of least action. It's sometimes called principle of stationary action because we are relying on the fact that the functional derivative of the left side is set to 0, but being a critical point doesn't mean that it's a minimum or maximum, so more accurate terminology is principle of stationary action. And this Lagrangian mechanics is rewriting Newtonian mechanics or other kinds of physics in terms of this calculus of variations format. So for example, if you have the Newtonian mechanics, you can write the Euler-Lagrange equation as L of q prime as 1/2 m q prime squared minus V of q, where Vq is the potential energy. Now you might recall that 1/2 mv squared, because q is the position. If you differentiate the position, you get the velocity. Derivative of the position is the velocity, and 1/2 mv squared is what we call the kinetic energy. So this Lagrange has the format of kinetic energy minus the potential energy. Okay, and to understand why this functional captures the equation of the Newtonian mechanics, we can actually show that, but before we do that, I want to point out that potential energy creates forces, right? If you have a ball that's high up in the hill, then the potential energy will make the ball roll down the hill, right? And at any point when you put this ball here, you wouldn't expect the ball to go up. If you just release the ball here, you would see that immediately forces will be created sending the ball downhill. So always the forces are created in the direction where the potential minimizes or potential decreases, okay? And at any point, the fastest direction of decreasing potential is given by the negative gradient direction. So you end up with this important identity that you often learn in physics too, that when you have a potential energy, then its negative gradient is the force created by the potential energy. So let's accept that we have learned this. Then we can actually use that to calculate the Euler-Lagrange equation by doing the writing down this Euler-Lagrange equation. Another complication here is that because Q is now a vector, think of this as like a three-dimensional vector, x, y, and z components. Therefore, you have to write down Euler-Lagrange for Q1, Q2, Q3, the three x and y and z components. But anyways, if you do that, then because if you differentiate by Q, this is considered as a constant, you only get the derivative of this with respect to Qi. So that's where you get this first term. And for the second one, if you differentiate this by Q prime, this is not a function of Q prime, so you just get to differentiate this. And if you differentiate this by Q prime, remember Q prime squared is like Q1 prime squared plus Q2 prime squared plus Q3 prime squared, and anything that's not related to Qi will be 0, and you end up with 2 times Q prime I. 2 and 1/2 cancels, and you differentiate that again by the time t, and you end up with this. But what is the second derivative of position? That's acceleration, right? So when you set this equal to 0, you end up with F equal to ma, which is exactly the Newtonian mechanics. Now, you might wonder, why do this when you can just have F equal to ma and solve it? Well, there are several reasons why you would like to have Newtonian mechanics in the form of Lagrange action rather than the second order differential equation. One reason is that sometimes when you have complicated coordinate systems, then writing the Euler-Lagrange functional, the Lagrange action, is a lot easier than trying to figure out how the differential equation changes. And therefore, often what people do is they would start from the Lagrange equation's new form in that coordinate system, and then they would derive the equation of the motion using the Euler-Lagrange equation. So that's one reason why one does it. And there are some examples in the literature. If you open up any physics textbooks explaining the Lagrange action, you're going to see some examples in terms of pendulums and springs and stuff like that. So once you see how this works in action, you would be sold that this is indeed a pretty good way to do physics. And the second reason is that when you do quantum mechanics or quantum field theory, they take this Lagrange equation and think about all kinds of paths that minimizes the action, but they also include the paths that don't minimize but still could happen after quantum fluctuation. So let's say if a particle has to go from here to there in the classical sense, and this is the classical path, then in quantum mechanical world, this might not be the only path that the particle takes. It might go something like this, and some of them might go like that. But there's a way to do quantum mechanics by putting some kind of probability that it has the highest probability closer to the classical path than the ones that go far away. And that kind of way allows one to do quantum mechanics, and it actually allows one to see the relationship between the quantum mechanics and classical mechanics. So that's another reason why people would want to write down the Lagrange action. Now, I only showed you what Newtonian mechanics is, but there are Lagrangians for general relativity. There's Lagrangians for many other kinds of more complicated systems. So hopefully after learning and seeing this Newtonian mechanics version, you can have easier time understanding the Lagrangians in other field of physics.